Okay? All right, so solutions. Remember from last semester, there are two types of matter. One can be separated by physical means and one cannot. If it cannot be separated by physical means, it is a pure substance. And within that category of pure substance, you have elements and compounds. And compounds can be separated by chemical means or decomposed. For instance, water. If I put an electric current through there, I can break down water back into hydrogen and oxygen. So those are compounds. And then, of course, elements cannot be decomposed any further or broken down any further because they're already in the simplest form, which will retain its properties. Obviously, an element has electrons and all that stuff, and neutrons and protons, but an atom is the smallest it can be and retain its physical properties. The second type was mixtures, which is going to be basically what this unit is over because we're talking about solutions. But mixtures, there were two types of mixtures. You had homogeneous, which was uniform in composition, looks the same throughout. And we generally will refer to, homogeneous, as a homogeneous mixture as a solution. And then heterogeneous mixture, of course, is not uniform in composition, and those were two subcategories of that were suspensions and colloids. Are y'all, is this ringing a bell from last semester?
Nope.
Oh, that's sad. Okay. Anybody still writing before I move? Okay. Within your types of mixtures, oh, that's the same one. I was like, what is going on there? There we go. Okay. Types of mixtures, solutions, of course, are homogeneous mixture. Any substance, solid, liquid, or gas that is evenly dispersed throughout another. It's not the same as a chemical reaction. Remember, when I dissolve something in water, it forms a solution, but it is not a chemical reaction because if I evaporate that water, I can get it back out. Okay. So solutions, some examples of solutions would be like saline solution. Salt water, basically, would be an example. Salt water. I don't know what saline is. Contact solution. How many of you wear contacts? Okay. And then the components of a solution is the solute and the solvent. The solute is what is being dissolved, and it's generally in a smaller amount. And then the solvent is what is doing the dissolving, and it's generally in a larger amount. And then, of course, remember from the water notes that water is considered to be the universal solvent. Why? Because it is what? Polar. Thank you. Water. Is that what you said?
Yes, ma'am.
Okay, you just said it kind of strange. Polar. It's polar. And that means it can dissolve other things, obviously, that are polar, but it also can dissolve ionic compounds, so that makes it the universal solvent. It's actually really hard to have pure water because it dissolves so much stuff. You actually have to go through and distill it to get it to be pure. Types of mixtures for heterogeneous mixture, we have suspensions. And of course, suspensions will, the particles will settle out unless they're continually stirred or agitated. Some examples that you can write in there are my pictures: muddy waters, Italian salad dressing. When you were kids, you probably took, most kids in their life had to have the little pink medicine or amoxicillin for ear infections, whatnot. You know, Mom always had to shake it up, or Dad always had to shake it up before you took it because it's a suspension. So if you didn't shake it up and you just pulled the liquid out, you're just getting the solute, or the solvent, not the solute. And then colloids are the intermediate particles. Their sizes are intermediate. They will not settle out, but it is not a solution. Some examples of colloids are things like shaving cream, and then one of the ones you're more familiar with is fog. Fog is considered to be a colloid. Okay? Colloids have two phases. They have the dispersed phase, which is the particles, the colloid particles themselves. That's dispersed. That's an I. And then this is actually supposed to be dispersing medium, so cross out. That's a typo. And basically, this dispersing medium is like the solvent. Okay? Colloids also exhibit something called Brownian motion, which is basically when you look at it under a microscope, you think they're not moving, but when you look under a microscope, they're moving around. Unlike living tissue that's moving around for different reasons, but particles have Brownian motion. Okay? So here, remember the colloids have a scatter light, the Tyndall effect, and I'm going to show you a picture of that in a second. Here are some examples of colloids. Jello is a colloid. Styrofoam is a solid foam, but it is a colloid. A lot of paints are considered to be colloids as well. Okay. And there's not really any gas colloids that we know of at this point in time. Here's the Tyndall effect. If you have a colloid, you'll be able to see that beam of light because it scatters it, but in a solution it passes straight through. So when you are driving at night, and it's a clear night, can you see your headlights, the beam, pass through the air? No. You can see where they land on the ground, obviously, or hit something, but you can't see the beam of light traveling through the air because air is a solution. Okay? But if it's a foggy night, can you see the beams? Yes, because it's scattering light. That's the Tyndall effect. And that's because fog is a colloid. Okay? So that brings us to the solution process, which is called solvation. Not salvation, solvation. And that is the process by which a solute dissolves in a solvent. When solutes and solvent are soluble in each other, in other words, they will form a solution, we say that they are miscible. Think of mixable. They form, they're mixable, they're miscible. Okay? If a solution does not form when you try to mix them together, it's said to be immiscible. So oil and water would be considered to be immiscible. And of course, if something's dissolved in in water, what do we call that? What kind of solution? Aqueous. An aqueous solution means that it has water. So saline solution would be an example of that, which is NaCl dissolved in H2O. Okay? So let's talk about the process. You see this next part that says like dissolves like in your notes. So what that means is when we're talking about like dissolving like, we're talking about in terms of its polarity. Okay? If something is polar, it will dissolve something else that's polar. It will not dissolve anything that's nonpolar. They don't mix. Polar can also dissolve ionic. Okay? So ionic will dissolve in polar, but ionic compounds will not dissolve in nonpolar. Okay? So somewhere on your paper, you can do it on the back, if you can squeeze it on the bottom, I do want you to write down the different types of solutions because kids tend to, unless you think you can remember it, then don't write it down. But sometimes kids tend to think of just a solution as being a solid dissolved in a liquid when in fact there are all types of solutions. So I'm going to pause the video for a minute and give you all a second to write. All right, so when we're talking about, this is not in your notes, we just want to discuss it, okay? When we're talking about ionic molecules dissolving in water, we call that they're hydrated, okay? Because recall that ionic compounds, when they dissolve in water, they dissociate or ionize. There's two different words you can recognize. Ionization is kind of, to me, more self-explanatory because they ionize and form ions. So when I dissolve sodium chloride in water, it doesn't stay as sodium and chloride stuck together. It separates, okay? I have sodium ions and I have chlorine ions swimming around separately, okay? So water is then attracted to it. The negative side of water is attracted to the positive ion of sodium, and the positive side of water, which is the hydrogen, is going to be attracted to the chlorine. So it kind of looks like this, okay? So we generally show it with 5 to 6 water molecules. This is big in AP. They want you to draw the particulate diagram so that you understand what's going on. But what's basically going on is, water looks like this. We got oxygen, which is much bigger than hydrogen, and it's a slightly negative side. And then these are the slightly positive sides because it's a polar molecule, so oxygen's hanging on to that electron more. So remember, that's where they get that dipoles, or slightly positive, slightly negative. So the sodium ion is smaller than the chlorine because it's an anion and it gave away electrons. So then what happens is we call this hydrated because it's surrounded by water. Okay? Does that make sense? Breaks apart. The solvation process. The polar molecules, dissociation does not happen. Okay? So we get molecular solvation. Okay? So that's sugar. Okay? So we have a sugar molecule, and obviously sugar dissolves in water because we drink sweet tea and Kool-Aid and coffee, and it dissolves. But it actually does not dissociate. It stays together, and the water surrounds the ends of it. Okay, but it does dissolve, but it doesn't dissociate. So it stays all together. Okay. Again, we're going to that opposite attract. When we talked about when we talked about bonding, we talked a little bit about interactions. Those would be considered to be hydrogen bonding dipole interactions between those. And then nonpolar, of course, they don't mix. We call that immiscible. And so the reason it doesn't is because water is polar, but the oil is nonpolar, so it doesn't have anything for the water to be attracted to. So that's why it layers. And oil floats on top because it's less dense. So that brings us to solubility curves, which we're going to talk about and what your homework is over. And that is, the solubility is the maximum amount of a substance that will dissolve in usually 100 grams of the solvent. Okay? There are 3 terms that we have to know, and that is, first of all, if a solution has less than it can dissolve, or you were able to dissolve more, we call that an unsaturated solution. Unsaturated. And an unsaturated solution means I could dissolve some more. Okay, so if I had some coffee and I put a teaspoon of sugar in there, it's not sweet enough, so I put another teaspoon of sugar and stir it up. It still dissolves because it's unsaturated. Okay, but if I kept adding sugar to my coffee, at some point it's going to stop dissolving, and that's when I would reach the saturation. So that is a saturated solution. The way that I know that I had a saturated solution is I would stir my coffee and I would still have sugar crystals in the bottom. They wouldn't dissolve any longer because I've reached my saturation point. So you're going to see crystals present when you're at the saturation point. And then a solution that contains more than it should, okay, is said to be supersaturated. And the way a supersaturated solution is obtained is you heat it up, dissolve more at that higher temperature, and then cool it back down. Okay, it is unstable. Okay, and if disturbed, it usually will form crystals. So the best example of these 3 things is I like to use is something that most of you are aware of and have used is going to a restaurant and ordering tea. Okay, so you go to a restaurant and you order sweet tea and they say, I'm sorry, we don't have sweet tea. So they bring you iced tea, already in a glass with ice, and then what do you try to do? Add sugar.
Add sugar and then
okay,
dissolve.
Yes, because some dissolves at a cold temperature. Some sugar will dissolve, but not enough for your taste. So you stir, and you stop stirring, and then what happens in the bottom? You get a layer of sugar. They're not crystals. I mean, they're crystals, but the sugar you added. So that means you have reached the saturation point of that tea at that cold temperature. Okay? Before you put any tea in there, before you put any sugar in there, you had an unsaturated solution because it will dissolve some. Then you pour your sugar in there, and you dump. You stir, and then you stop stirring, and then sugar goes down to the bottom. So that's a saturated solution because no more would go into solution. However, if you were to make sweet tea at home, what do you do to make sweet tea at home? You boil the water, and do you put the sugar in while the water's hot or when it cools down? While it's hot. Okay? So you put the sugar in there while it's hot, stir it up, and then you pour it over ice. So now you have a supersaturated solution because now at that temperature of the iced tea, it's got more sugar than it should have in it, okay? If you were to let that pitcher of sweet tea sit for long enough, it actually would recrystallize out. If anybody's ever gone on vacation and left a pitcher of sweet tea in there for like 2 weeks, you come back and there's usually sometimes a layer of sugar at the bottom and a big crystal. Yes?
So if you have like sweet tea and you pour regular sugar and it doesn't dissolve, that's saturated, but you can also add like another packet and it's still just saturated.
It's still just saturated because it won't dissolve anymore, okay? Pretty much the only way to make a supersaturated solution is heat it up, dissolve more than it should have, and then you cool it back down, okay? That's how they make rock candy. You can go home and make rock candy this weekend if you want. Go home, boil a cup of water, dissolve 2 to 3 cups of sugar, throw some extract in there if you want to give it some flavor, and then get you a jar and pour it in there, put like a string or a stick as a seed, and put a seed crystal in there and let it sit for a couple of days and it'll grow crystals. Yeah, that's how you make rock candy. Now the candy stores, they make it a lot prettier. It won't turn out that pretty at home. It never does, but that's how they make rock candy. It's just they super saturated solution and then cool it back down. Okay. So that brings me to the solubility curve, which looks like this. Okay. Whoops. Sorry. Hit the wrong button. Okay. So in the solubility curve, remember I said when we're talking solubility, it's usually per 100 grams of solvent, which is water. Okay. And then as you can see with the temperature, the solubility changes. Okay. And then it's grams of solute per 100 grams. So if I was looking at this and said, okay, at 40 degrees, how much sodium nitrate could I dissolve? What would you tell me? About 105 right here, right? About 105. Okay. So that would be its saturation point. 105 grams of sodium nitrate and 100 grams of water is a saturated solution. When you're on the line, it's saturated. That's the maximum amount. Okay? If I told you at 40 degrees Celsius, I dissolved 80 grams, would be right there. Okay? That is an unsaturated solution because I could still dissolve some more, correct? I could still add some more. Okay? What if I told you I dissolved, I heated my temperature to 80 degrees and dissolved 140 grams. Wait, and then I cooled it back down to 40. Now I'm up here. So I heated it up and then I cooled it back down. So now I'm supersaturated. I have more at that temperature than I should have. Okay? So I could figure out how much would crystallize. How would I do that?
Minus
140 minus 105 means 35 grams would crystallize. How could I what? Because I said, we said it was 140. I said a 140, right? Yeah, 140. But I cooled it back down. At 80, 140 should dissolve. Well, I should have said 90. You get the gist. Okay, you get the gist of it. Okay, so that's how you read a solubility curve. Okay, if you're on the line, you're saturated, your maximum amount. If you're below, you're unsaturated. I could add some more. If you're above, you're supersaturated. Okay, supersaturated. Okay. So factors affecting the rate, not how much, the rate. So make sure you know that this is a rate, not how much. Okay.
so many words.
This first one is stirring or agitation. So when I have a water bottle and I get my little packet of, I don't know, Crystal Light to put in there, okay, do I just dump it in there and let it sit, or what do I do to it? I shake it up, because if I don't shake it up, it takes a really long time to dissolve. And the reason that that works is because when you're shaking it or stirring it, you are introducing fresh solute solvent particles to each other. Okay, so if I have this and this is my water, and I just dump my sugar and I got all these particles, the only thing that's interacting with these particles is this layer right here of water. Okay, so you want to stir it. because you want to, the more that you can introduce the molecules of solvent and solute to each other, the faster the dissolving will happen. The other one is to increase the surface area. So by increasing the surface area, I have more particles of solute and solvent interacting. So let's say I have this and I put a sugar cube in there, okay, and I just wait for it to dissolve. It's going to take a long time because the only thing that is dissolving are the particles right around the edge. I got to dissolve layer by layer by layer, so it takes longer. But if I crush it up and I have more surface area, it will dissolve quicker, okay. And then increasing the temperature. If I increase the temperature, it generally will dissolve quicker. Now, may or may not increase the amount, because some things actually decrease their solubility or pretty much level, but it will definitely cause it to dissolve quicker, okay? And be careful with surface area, because sometimes people, kids will think increased surface area means it has to be big, okay? You want, when you're thinking when you crushed, so if I took that sugar cube and I lay it out, it doesn't have that big of a surface area, but if I crush it up and then spread it out, thin layer, one crystal at a time, it has a really large surface area, so it would dissolve quicker. So basically the way to remember that is heat it, crush it, stir it. Heat it, crush it, stir it, that affects the rate. Okay? So crushing it is your increasing of your surface area. Factors that affect the solubility, this is affecting how much will be dissolved. First one is increasing the temperature. Generally, increasing the temperature will increase the solubility of your ionic compounds, generally. But if you look down there at NaCl right here, it's actually pretty, it actually goes very little change. Okay. And then this NH3, see how much it goes down? That's NH3. It's because that's a gas. And we'll see in a second that gases have the opposite when you increase the temperature. Okay. Decreasing the temperature will increase the gas solubility. Okay, so if you're trying to dissolve a gas in a liquid, you want the temperature of the liquid to be cold. Okay, and that's why you should store your Cokes in the fridge before you drink them. Okay, because it'll actually stay fizzy longer. Hot Cokes will go flat much faster than cold Cokes. Or Dr. Pepper, or whatever else it is, it's carbonated. Sprite, 7-Up, whatever. Okay. So this is a chart. CO2 is a big difference. The oxygen is a lot less pronounced, as is the nitrogen, but the CO2, which is what's in carbonated beverages, goes down tremendously as your temperature increases. So a hot Coke goes flat really quick. And then pressure. And pressure only affects gases in liquids. Okay? Because kids will miss that on the test. It only affects gases in liquids. And it's, you do not have to do calculations with Henry's law, but you do have to know that they are directly proportional to the pressure above the liquid of the gas. So the more pressure above the gas, the more, above the liquid, I mean, the more gas that goes into the liquid. So, example, when you open a Coke, what sound does it make? Okay, that's because on top of that layer of your Coke, that's pressure. It's pressurized, and it forces that gas to stay in there. That's why when you just have a Coke bottle sitting there and you haven't opened it, you don't see the bubbles escaping. Okay, but as soon as you open it, then if you sit there, you can see the bubbles start to escape. Okay, but you have to know that it's directly proportional to the pressure on top. If you put more pressure on top, you get more particles of gas dissolved in your liquid. Solution proportions, very simple. If you have a relatively large amount of solute, you have a concentrated solution. I used to not put this in the notes, but then kids were missing it on tests, so I had to put the simple things in there. Concentrated means you got a lot of solute relative to solvent. If you have a small amount, it's dilute. Can you see my eye there? Now you can. Dilute solution. Okay? So a trend probably about 5 years ago was the concentrated, all the solutions concentrated. Like now we have Tide Pods instead of the big thing of Tide. Or you got the little Cascade packets, it's all concentrated in there. Okay? And then this is the last thing in the notes today, electrolytes versus non-electrolytes. Electrolytes are compounds that will completely dissociate and they will conduct electric currents, either in their molten state or when they're dissolved. So electrolytes are conduct an electric current. Salt water would be an example. Okay, salt, that doesn't look like salt water. Let me look at that. Salt water will conduct electric current. Strong electrolytes are aqueous solutions of ionic compounds, like NaCl. Strong acids, which were in your net ionic equations, and strong bases. This one is left off on this list, HClO3. HClO3, some texts say it's a strong acid, some do not. AP Chem actually does not list it as a strong acid, so I tend to leave it out, but it was on that other paper. Your strong bases, of course, are your group 1 and 2. And then there are things called weak electrolytes, and they are things that only dissolve a very slight amount, and they will conduct a very small, weak current. Acetic acid vinegar is an example. Okay, ammonia is an example for a weak base. And then you have your non-electrolytes. They don't dissociate. They don't conduct electric current, either melted or whatever. Remember we did that lab where we tried to do the current of certain things? Sugar water would be an example. Sugar obviously dissolves in water, but it does not conduct an electric current because it's a non-electrolyte. And that's where we end today.